I'm going to tell you about genome-wide association analysis significance and tell a few words about coverage and another concept which is very much related to power, the coverage. So definitely when we do genome-wide association analysis we are in the situation of multiple testing, and then the question is, of course, what nominal p-value should we consider significant? So experiment-wise alpha, experiment-wise type 1 error rate is 5%. And in the first lecture I was talking about Bonferroni correction, and according to Bonferroni correction, to have type 1 error rate of 5%, the nominal p-value to make decision about significance of association should be 5% divided by the number of tests. But there is a certain problem with the Bonferroni correction when you think in the context of genome-wide association scans, and I would like to ask you a question: why using Bonferroni correction may be not that good idea for genome-wide association scans. So the thing is that as the assumption of Bonferroni correction is that we are performing independent tests. However, in the genome there is linkage disequilibrium, and therefore SNPs are correlated and their tests are not independent. What happens in this case? Well, assume you are testing, let's consider a very simple situation. You are testing association with two SNPs, right? If they are on different chromosomes, they are not correlated, these are going to be two independent tests, and the Bonferroni correction would be a very good way for multiple correction. Now imagine that your SNPs are very close by and there is a very strong linkage disequilibrium between them. And if you take the situation to the extreme, there may be a perfect linkage disequilibrium between you two SNPs, meaning that the genotype of one SNP can predict, perfectly other SNP. So statistically these two SNPs are the same, and they have correlation of 1 or -1, doesn't matter, coefficient of determination of 1, and then you get exactly the same test statistics from both tests, and effectively you are doing only one test. So of course in this situation the Bonferroni correction would be a bad method to deal with multiple testing, and it's going to be a conservative correction. So you're forcing your results, which are actually significant, into the area where they may become not significant. So one method which is currently being used is multiple test and burden correction, and the idea of this method is very neat. So the authors of this paper published in Genetic Epidemiology asked the question: if we were measuring all common SNPs in the genome, and the number of these common SNPs in human genome is about 10 millions, how many effective tests we would be doing? And by effective tests we mean that while these real tests, 10 million tests, may be correlated, what would be a number of independent tests corresponding to the same level of correction? So what they found out is that if you measure all common polymorphisms in human genome, this corresponds to approximately 1 million of tests, independent tests, and therefore to keep type 1 error to 5%, you should I use a nominal p-value with a Bonferroni correction of 1 million. So that would be 5% divided by 1 million is 5 by 10 to the minus 8. So if in your genome-wide association study you obtain association with p-value which is less than 5 by 10 to the minus 8, you may consider this result significant, and this should correspond to type 1 error of 5%. Now, there is one thing which you should keep in mind when you use this threshold value. Of course, it depends on the amount of linkage disequilibrium which is present in the genome of the population. And this number of 1 million of independent tests was obtained for the population of European descent. If they used the same methodology to figure out the number of independent tests in African data, so this is our data which are present in HubMap population, Yoruba, Ibadan, then the number of independent tests was 2.5 million. So this sounds like a large difference, but effectively, if you plug in 2.5 million instead of 1 million in the denominator of Bonferroni correction, the difference will not be that huge. So sometimes when you obtain results which are kind of boundary significant, so they are either a little bit less than 5 by 10 to the minus 8 or a little bit more, you're really not sure if your results are true or not, and then the only way to convince yourself, and of course to convince the reviewers of your paper that your results are significant, is replication. And replication is the way to achieve a really good significance, and also by doing this replication in independent sample, you exclude the possibility that your results have been your study population specific, while there might have been something, you know, very special in your design. So if you want to generalize your finding and make it stronger, you definitely want to do replication, and replication is indeed considered as a must in current genetic discovery procedures. So here I provide an example of, this is imaginary or simulated example of replication. So in the original study, we, for certain SNP, we observed a beta value, the effect of 4.6, so that could be, let's say, 4.6 millimeters of height, and standard error is 0.88, which would give us p-value of 2 by 10 minus 7. So this is not really genome-wide significant, but when we look up the same SNP and association of the same SNP in 3 replication populations, the nice thing is that the association goes in the same direction, and then so in one population we don't even obtain nominally significant results. When we combine all this in meta-analysis, the joint p-value is 2 by 10 to the minus 11. So this is, to me, very convincing p-value, and it's smaller than 5 by 10 to the minus 8. So you can claim genome-wide significant association for this SNP. And without these replication samples, that would not be possible. Now I'm going to tell a few words about power of genome-wide association studies, and I will jump directly to this table. And what I show in this table, that when you have certain sample sizes, 1,000, 5,000, 10,000 individuals, and your SNP explains a certain proportion of variance, which I vary from 3% to 0.1%, how much power you have to find the association to this SNP at the genome-wide significant p-value. So why do I pick up this 3% to 0.1%? Why I never consider the scenario of, say, 10 or 20% of variance explained by SNP. Well, this is based on our knowledge about what we find in genome-wide association studies of complex traits, and here are examples for traits I know because I have been working with them. For example, for lipid levels, the strongest locus we know is locus for HDL, and some variants in the CETP region explain up to 2.5% of variance. And in complex genetics, 2.5% of variance explained is considered as really big effect. And you remember in previous talk I demonstrated a Manhattan plot for HDL, and you remember that with roughly 20,000 samples we obtained p-value of 10 to the power of minus 100. So 2.5% is really big effect, and you shouldn't count that you are going to get much larger effects if you analyze complex traits. So this is why I take 3% as upper limit of what I'm going to consider. And again, if we go back to lipids and look in total cholesterol, then the biggest locus, and that's ApoE, would explain only 0.5% of variance. And then if you take an example of height, then the biggest known locus, HMGA2, explains only 0.3% of variance. So actually you should expect that for complex trait, if you do a GWAS, you're likely to find that your strongest loci explains 1% of variance or less. So let's look what kind of power we have to detect loci explaining different proportion of variance when we have sample sizes of 1,000, 5,000 to 10,000 people. So you can see that with 1,000 people, even for a locus explaining 3% of variance, which is like big locus for complex traits, you have only 51% chance that you will see it in your GWAS. So this is almost like coin tossing. So with 1,000 you have very little power to detect even big loci, and if you go to 1% and less, you see that your power is really miserable. When your sample sizes increase to 5,000 individuals, you have very good power to find really big effects, and you still can detect reliably a variant which would explain 1% of variance. But if you go down to 0.5, 0.1, your power becomes really low. And you remember for height, the biggest locus explains 0.3% of variance. So if you study height in sample of 5,000 individuals, you're not likely to see even this biggest locus. Then with 10,000 people, you get relatively good power, already down to 0.5%, but again, if you're looking for really small effects like 0.1%, you have no power at all, and you would need to increase sample sizes even further to detect loci of this small effect. Now I'm going to tell a few words about a concept related to the power, which is the coverage of genome-wide association study. And the coverage really depends on what type of what SNPs you have on your SNP array. So to explain the concept of coverage a bit, here I demonstrate results for a simulation experiment, and I modeled a variation in a small genomic region, and then I mimicked the selection procedure for SNPs. It was mimicking the procedure which was used to pick up the SNPs which are present on genome-wide association SNP arrays. So these SNPs which I picked up for my imaginary array are indicated with red bars, and then there is linkage disequilibrium in this genomic region, and therefore for certain SNPs, though they are not presented on my SNP array, they may be in very strong linkage disequilibrium with SNPs on the array. So I'm going to capture this variation through the linkage disequilibrium. And these variants I depict with a green bar, and the height of the bar corresponds to what is the linkage disequilibrium, what's the value of R square linkage disequilibrium metric, which I achieve for this SNP between this SNP and one of the typed red SNPs. And then in blue are SNPs which are poorly captured with my genotyped SNPs. The R square is between 80 and 50%, and then in black I show the SNPs which are really not visible when you type these red SNPs because they have only very low linkage disequilibrium with the typed SNPs. It's worth to note that by design most of these SNP arrays contain common variants, and by definition of the linkage disequilibrium metric R square, something common cannot be in high linkage disequilibrium with something rare, and other way around. A rare SNP cannot well tag a common SNP. So from this graph you see that all my red SNPs, the SNPs which are on the array, they are common or relatively common, and they have potential to tag only common SNPs, while the rare variants which are present in the genome are not well tagged at all. Here I am going to present the coverage numbers for a few standard panels. Unfortunately, this slide was not updated for a while. Currently we have bigger arrays, and here by coverage I define the proportion of common SNPs which are either on your SNP array in the genotype set or are in high linkage disequilibrium of R square of 80% or more with at least one of the genotyped SNPs. And you can see that nowadays we use arrays which have 1 million SNPs or more, and the coverage is 80% or even more than 90%, meaning that these arrays manage to capture a large proportion of the common variants which are present in human genomes. Well, note though that these coverage figures are given for different populations, and actually depending on the population the coverage could vary quite a bit. And this is quite visible for Illumina 300K array, which has 75% of coverage for European populations, but only less than 30% of coverage for Yorubans, for African populations. And this happened because this chip was specifically designed to capture the variants in Europeans, while in Africans and also in Asians the structure of linkage disequilibrium is different and it works not so well. Okay, nowadays we use SNP arrays which contain close to 1 million or over 1 million of SNPs, and we do have rather good coverage of common variants for any human populations. So the numbers vary from 80% and more, so that's not so bad. And for some diseases and traits you may expect that they are expected in large part by common variants, but for other diseases, of course, multiple rare variants may play an important role. And you should keep in mind that with the SNP arrays which are designed to capture common variation, they are not capturing rare variation. Well, right now, for European populations, exome chip was designed to specifically capture rare variants, but that's a slightly different story, and this type of designed chip would not work for other populations, because specifically rare variants, they are very different between different populations. I gave you a few figures for power, but you may want to compute power yourself for your specific sample. And then there is this great tool available on the web. So if you just go to Google and type genetic power calculator, you are going to land at this page of genetic power calculator, and then you can choose your design and fill in the forms, what parameters you expect for your polymorphisms, and it's going to give you back the power you have for your study. Very nice tool.